Hello, so we are One and today we would like to present our mini project. So this is our team member which consists of 3 members. So let's start with the task 1, exploring the collected data. So our dependent variable YT represent the advanced retail sale. We also collected the independent variable which include employee number in the different retail sector and the consumer price index. The datasets cover the period from January to the November of 2025, ensuring all variables match the same time frame. And here are descriptive statistics for our cell variable. First, the mean is greater than the median, which indicate our data is right. And second, the standard deviation is high and the coefficient of variation is over 39%, meaning the data fluctuates strongly. And finally, the range is very large, showing that the data is widely dispersed. So we then test the probability distribution of the data. So please look at the graph called the normal probability plot. The blue dot represents our data and the red line represents a perfect normal distribution. Since the blue dot curve away from the straight red line, we can confirm that our data is not normally distributed. And because the normal distribution didn't fit, we test other model to find a better one. So on this slide, we can see that our 4 different graphs, we compare the goodness of fit using the ID score. The lower the score, the better the fit. So the 3-parameter Raman distribution gave us the lowest score, and therefore we conclude that the Raman 3P model is the best fit for our data because it's handle the skewness better than the other. So moving to task 2, we analyze the component of the time series. Looking at the graph, we see a strong linear upward trend from 1992 to 2025. There's also clear seasonality. Sales always peak in December and drop in the January and the February. And importantly, the seasonal wave get bigger as the trend goes up. This abandoning the pattern means we must use the multiplicative model. So to calculate the forecast, we consider 3 methods here. The first one is the whole winter multiplicative model. We chose this because this is specifically designed for data with broad trend and expanding seasonality. The next one is the seasonal ARIMA. This method is good for capturing the complex pattern and the relationship in the residual. And the last one is time series decomposition, a simpler method that separates the data into trend, seasonality, and the random noise. So after running the calculation, we compare the accuracy of the method here. So as you can see in this table, we look at the MAP. The winter method has only 2%, where the decomposition method has 8%. So therefore, the winter method is the best choice for this dataset. And using the winter model, we generated a forecast for the next 3 periods. So the results show a continuous upward trend, especially for the period for 408. The forecast jumped to over 700 million, which indicate a seasonal peak, and the narrow gap between the upper and the lower limits shown in the table tell us that this forecast is stable and reliable.
I will now walk you through the regression model process, the adjustment we made, in our final results. To construct a forecasting model and effectively explain the fluctuations within the target series YT, our team has screened and selected 5 independent variables for analysis. This is the list of explanatory variables include H1T to H5T. The integration of these variables is intended to capture the multidimensional impacts of the labor market and consumer price indices on the trajectory of YT. To continue the multivariable regression analysis, we first generate the missing value for x60 using a uniform distribution and then convert the CBI series into a categorical variable as required. Next, we ran the full regression model. While doing this, we identified two major statistical issues. First, the variable x60 had a p-value much higher than 0.05, meaning it is not statistically significant. Second, we found self-multicollinearity. The variable x2t had a VIF of 22 and the x5t had a VIF of 12. Since this is above 10, the model is unstable and needs refinement. To fix the model, we follow a two-step procedure. The step 1, we remove the non-significant variable x60. However, the multicollinearity remains high for x2t. So in the step 2, we remove x2t, which had the highest VIF. The result is this successfully solved the issue. As you can see, the VIF for all remaining variables x1, x3, x4, and x5 drop below 5, meeting the safety threshold. After refinement, we established our optimal model with 4 independent variables x1, x3, x4, and x5. Finally, we validate the model by statistical testing. All 4 variables now have p-value of 0, confirm they are statistically significant predictor. And by multicollinearity VIF, all the VIF value in the final model are below 5, confirm no remaining multicollinearity. And the last one is the key observation here. The sign flipping is x5t. Initially, it had a negative coefficient by negative 113.8, but after fixing the multicollinearity, it flipped to a positive 793. This proves that removing the multicollinearity variable restores the true positive impact of x5 on ourselves, and it also is the strong evidence that the model refinement process were necessary and correct.
And now let's move to task 4. First, we have to look at the time series plot of YT. The data shows strong upward trend and clear seasonality because the series form a repeated sawtooth pattern and the variance increase over time, creating a funnel shape. This means the data is non-stationary, so we must transform it before building a model. So in the first step, we apply the first difference to remove the trend and make the series more stable. And you can see that after differencing once, the trend becomes smaller, but the seasonality still remains. So we have to apply a seasonal difference of 12 months. And this step removes the repeating yearly patterns. And now you can see the data fluctuate around a constant mean and variance. So that we can see that the series is finally stationary. So which is required before we choose an ARIMA model. And here is the ACF difference of different data. We can see a strong negative spike at lag 1 and another spike at lag 12. The spike cuts off quickly, so this suggests an MA structure in this model.
And this is the PSF of the difference data. We also see a significant spike at lag 1 and lag 12, but the other lag die off slowly. This behavior is consistent with MA type model, so after analyze ACF and PICF, we select the seasonal ARIMA 0110112 model. And here's our result after using this model. And first let's look at the Chong-Bot test. We can see that the p-value is smaller than 0.05 because the reason is the real conditions of the data. So, but the visual residual ACF show no strong remaining pattern. So the model is adequate for short-term forecasting, which is follow the Bokchin-Skin rule. And here is the forecast for the next 5 periods. We can see the forecast value is continue the upward trend and show the usual seasonal pattern. We include 95% confidence interval to show the possible range for future value, and this interval help us understand the risk and uncertainty, which is important for planning. And this is the end of our presentation. Thank you for watching.